You're all set. I'll be back.
Never. Never coming back. Cool. So James said last time you guys did like all the student stuff, right? You guys have done the student class, that's all. Okay, cool. Neat. So I guess from here, hi. He's up there. He's sick today. So I'm hanging out. Don't sound so excited about it.
No.
Yeah, no. Cool. Yeah, so today we'll start with the course class, which essentially is going to be, as you can probably read, a collection of a bunch of student objects. So basically, the students in a course will be stored in the list, and we want to build the course class to have some special functionality that you would probably want from a course class. So basically, we're going to write 5 methods to add a student to the list that is the course. We're going to remove or add a method to remove a student from the course, add a method to get the size of the course, which would just be the number of students that are in the course, and another method to check if the student exists in the course or if they're enrolled, and a repr method just to stringify the course. So yeah, that's the course class. I guess we can just get this into the same folder. So as you guys probably figured out, obviously this is only the constructor. It basically just takes the name of the course as the input and assigns that to the self.courseName variable. The second, or line number 9, is you're basically just initializing a list. You're creating an empty list and assigning it to the private variable _students. So I think James probably went over it a little bit before, but private variables basically are only supposed to be referenced by the object itself. You're not supposed to be able to use them outside of the object. So if you create a course, that is a course object, and I guess we can do this class. So you should be able to do this. So you should be able to reference non-private or public attributes like course name. There's no underscore in front of it. So this line, perfectly fine. That's typical. You're allowed to do that. You shouldn't ever be referencing any attribute with an underscore. So .students as an attribute is only reserved for the class itself to use in however you guys as implementers of the course class deem fit. But I digress. So yeah, that basically covers this bit. You don't want to be accessing the list of the students directly. You want the class to do all the work for you, and you basically just want to be able to get the things from the list that you want with the methods that you're going to write. Yeah, it's just a convention. You'll see it in a lot of programming languages, especially when you get to the point where you're dealing with other people's code and other people's classes. The underscore in front of variable names is very, very, very common, and it's assumed that you will never be referencing any variable with an underscore in it. But anyways, so yeah, moving from the constructor, we're going to do the size and the adding. Now, as you guys can probably tell by now, the size for this list of students that are in a course is just the length of the list. If you're wondering why can't we just use length, you can. But in all other, or the majority of other programming languages, len is not a function that exists. You don't get access to it, so you will have to make your own. if you do 162 next semester, you'll be using Java. Java doesn't have a len function. So you actually have to write the size function yourself, where you'll iterate through and just count the number of things in it, because that's all that len does, is it takes a list and it just counts the number of things that are in it and gives you the number. So, and for example, like for work, if you're implementing a class and somebody says, oh, I want it to have a size and an add function, they don't care how you implement it. They just want it to be called size and they want it to be called add, which is why you have, even though obviously len and append are both methods in Python and functions that you guys use a lot and you will have been using and you're going to use, you have to nest them kind of in these other functions that are very common. They're very common in like most classes where you're dealing with any sort of data structure like a list. So that's basically why, even though you could just call the length of the students, you could just get the length of the private attribute. Because we shouldn't be referencing a private attribute, you can just return it in a separate function. And adding the same thing, like you just take the list, you just stick another student in at the end, they're now enrolled in the course. Now, when we're,
Go back up a little.
Yeah.
Does that mean, so the variable student is of the class student? Is that all it's saying? Like at the very top of the def add cell?
Yes.
Okay.
Yeah. So the course, so the list of students, that's like the private attribute or whatever, is only ever going to be a list of instances of this class.
Okay.
So you'll make like student A, student B, student C, and then a course can be like a course add student A, add student B, add student C, and it'll just append them into the list.
Okay.
Yeah. Anyone else have any questions before? Okay. Cool. So, so moving on to, we're obviously, if you have a course and someone drops a course, you want to be able to remove them from the course list. I'm sure you guys don't want to be getting emails from a course that you're not taking. So, basically, to remove a student, you have to check, one, that a student exists in the course, because if a student doesn't exist, you can't remove them, and then you have to remove them. So, basically, I'm sure it sounds familiar to all you guys at this point, but checking if a thing exists in some other thing is basically just a linear search. To avoid writing a linear search however many times, we're going to write a find method. So this does exactly what you think it's going to do. It'll, given a student, it's going to check if a student exists in the course. Are they enrolled? If they are, give us the index. If they're not, return what's called a sentinel value. Sentinel value is basically just a fancy way of saying, if we haven't found something, return this value. In maybe more complex classes, you might have like global variables set to just equal not found. Not found. And instead of having return -1, you would just have return not found here. Cool. So yeah, we've got the constructor, which is basically just tells us what the name of the course is and then creates a private attribute for the list of all the students that we're going to have. The size, which is just the length of the course, because as the course is represented by a list, if you take the length of it, that's the number of students that you have. Or you can assume that the number of students that you have is just the length of the course. Adding a student, you just append a student to the end of the list. And find, you want to basically do a linear search, find if a student exists in the course. If they do, return where in the course they exist, at what index. And if they don't, return -1. We can create another variable here. So this would be like, you can create self.notFound, have that equal to -1, and then instead of just returning -1 here, you can just return self.notFound. You can do it either way. It's more up to however you guys feel like implementing it, but I mean, that seems a bit easier to read, I guess, than just returning -1, because -1 could just be some arbitrary value that somebody decided to set. But if you have an attribute set in the constructor, you can then reference it again in other functions and use that kind of, instead of having to write a comment saying, this wasn't found, so I'm returning -1, you can just, that kind of speaks for itself. Another thing is find also comes with an underscore in front of it. This is because find is a private method and should only be used in other methods in the class, as we will see with return and contains. So, yeah, as you guys have already implemented the student class, find will check, it'll basically loop over all of the students that the course contains, and using the equals method that you guys would have written for the student class, just checks if the current student that we're at while we're looping is the student that we're looking for. If it is, just return the index. If it isn't, then return some not found number. Yeah, find is just a linear search. It's not really anything special. You guys could probably do it with your eyes closed at this point. And because we've written find, contains and remove now get condensed quite a lot, because we don't actually have to do any of the searching in these values, or in these methods. So contains, you just run, so checking if a student is in a course, just now returns a Boolean. If we're able to find a student in the course, then this returns true, and the course contains the student. For remove, we want to check, we want to check that a course contains a student. If a course doesn't contain a student, you just raise your own error, and then you can say, oh, okay, well, this student doesn't exist in the course, so you don't get an error. You can write your own errors, basically. You guys have probably covered errors before, but when you're, say, adding when you're adding a string and an integer, the error that you get is going to be so instead of type error, we would be raising a value error. And the text here, somebody wrote, so somebody who is a lot more involved with the backends of Python than I am, wrote a function like this for the plus operator to basically say, make sure they're the same type. If they are, add them. If they're not, raise a type error. So that's all remove is doing, is basically doing the same thing. You're checking that a student exists in a course. You're checking that there is something to remove. If there is something to remove, just take it out. If there isn't, make sure we raise an error and say, well, it doesn't exist, so I can't remove it. And this raising an error instead of just ending the function or just returning -1 is so that people who aren't you that are using your code, or you in, say, a year, if you come back and look at it, can be like, oh, okay, I'm going to try something, and if it doesn't work, you'll get an error that a student doesn't exist, and that's much more, it explains what's going on in the code a lot better than just printing -1. Because -1 doesn't hold a lot of meaning outside of it's not found. But in a year, you guys might not remember that that's what you set it to. So raising a value error is just much more kind of explicative of what's actually happening. We can put these in there too. so if a student isn't found, raises an error. Yada yada. Anybody have any questions about errors or anything? Yeah. All right. Yeah. You guys can all of like the raising errors. You can do like try and accepts and raise errors. You can. There's a bunch of different types of errors. You can just raise a general error. You can raise type errors. You can raise value errors. There's lots of different ways you can use them, and they can be very helpful in trying to help you debug your code as well. Cool. And now, yeah. So we've done add, remove, contains, and size. So we've done kind of the four main functionalities that we want our course to have, and now we basically just want to print it. So you can implement this kind of however you like. If you wanted to print like the course name and then print all the students that are in the course, if you just wanted to print the course name and not print anything about the students, you can. But the way we're going to implement it is basically doing string building. Where we're going to start with an empty string and then loop over all the students in the list and do string building. Just take the string representation. So that line that's highlighted calls the repr of student. So the method that you guys all wrote already previously will be called here. You'll get the string representation of the student, and then that just gets added to the string that you will then be returning. So you just add, for every student that you have in the course, you just add their string version to a string s, and then you just return s, and that's basically all, that's all the repr is. You can change this and do whatever you like with it, but for the most part, that's really as complex as it gets. So, based on, I guess, this student repr, that's too far in. Cool. So, based on the student repr, and the repr of the course, when we're printing the course, we're going to basically just get the first name and last name of the students, because that's all we're telling it to do in the student repr is take the first name, or take the last name, take the first name, and then the student number. Put that value, like fill this student in the repr with the string value from the repr, from the student's repr, and then just add it to a string. So that basically just ends up giving us this, which you get Smith Bob instead of Bob Smith, and then the student number after a tab. So you can actually change the student repr and change how the course repr functions. If we put, say, I don't remember what that character's called, but if we put a big line in that one, and separate the first name, the last name and the first name by a comma, and the first name and the student number by a line, it now updates the repr, and we didn't touch anything in, we didn't touch anything in the course repr, but the output's changed because we've updated the repr of the students that's getting called at line 45. Does anybody have any questions about how to use a class inside another class or anything that's happened? This is basically everything you'll need to do. Well, not everything, there's other stuff, but like the idea of this is what you'll have to be doing for your fourth assignment, where you're using a class inside another class. So making sure that your student function, or that your student class, like the repr works the way you expect it to, and the equals works the way that you expect it to. If this equals didn't work, then we wouldn't be able to find students properly. We might find students that don't exist. We might not compare students. If two students have the same first and last name but a different student number, it might count them as the same student, which you wouldn't want. So everything in the student class is, if you assume that it's working properly without testing it, it can really trip you up when you start using it in different ways, like in the course class. So aside from checking the size of a course, adding a student to a course, removing a student to a course, and checking if a student is in a course, and how to print the course as a string, do you guys have any other things that you would want to put in here? We can just try and adding some different stuff and just see if it works. Yeah.
If we have like two courses, we could still get students in either or both.
Yeah, like check, okay, yeah, so if you had like computer science and like math, just check if a student's in both courses.
Yeah.
Yeah. I don't. So we could do that as the equals method. So yeah, I guess we could do that as the equals method, where we would take another course and then we can take a student and basically just return if self contains and so this is going to be returning a Boolean, because the equals methods always return Booleans. And basically all it's going to do is it'll call contains student on itself, and it'll call contains student on the course that we give it. So if we have my course and your course, and this is Math 101. And in your course, we want to add Bob Smith, but we're also going to add Jeremy Johnson. Sure. And we're going to make sure these two have different student numbers. So here. Oh, also close. Your course. I wonder where I didn't close a bracket. Okay, I guess we're just gonna start with 0. Cool. So yeah, we've made Computer Science 101 and Math 101. Computer Science has 4 students in it: Bob, Jane, Niles, and Jane again. And Math 101 has Bob and Jeremy. We can probably update the repr of the courses, so that when we're printing multiple courses, we know what course we're talking about when we're looking at the list of students. So we can take self.coursename and print that here, and put \n at the end, so it creates a new line. And I guess we can run that again. Cool. So yeah, for Computer Science 101, we've now got 4 students, and for Math 101, we've got 2 students. If we want to check if my course is equal to your course, my course dot your course, and let's check. Well, I mean, we can check Jane, and I mean, obviously you guys would know by looking at the list of students, Jane only exists in Computer Science 101. Oh, neat. Oh, that's why. Okay, cool. Neat. So, obviously, when you're in a class, make sure all your functions have self at the start of them. But anyways, yeah, we can now go back and put Jane back in here. Cool. So we can check and see if Jane is in both courses, and we can also check and see if Bob Smith is in both courses. Bracket. Nice. Cool. So, yeah, obviously, as I'm sure you guys would have figured out just by looking at these, obviously Jane only exists in computer science and isn't taking math this semester, so she doesn't exist. It's false. The courses regarding Jane are not equal. With true, well, Bob Smith with this specific student number exists in both courses. Yeah, thank you. Cool. Does anyone have any other things like that you would want your courses on? Like, are there things, I guess as students, are there things that your courses don't do that you wish they did in, like, say, Moodle, or things that your courses do that you would want to see how to maybe write that out in Python? Okay. Well. Yeah, so I guess that's basically everything for the student and the course class. So we can look over the unit tests and go through these. Do you guys want to go through the student and the course unit tests, or like just the course ones? Or just no preference, I'm assuming? Yeah, okay. We can start with the course ones. We can do the student ones every time. Cool. So, testing the courses. Basically, this test, kind of self-explanatory. You want to check that it's returning the correct name and someone isn't basically hard coding the name of the course. So, for that test to fail, we would need, instead of setting course name equal to the parameter that's being passed when we create the course object, we would maybe change this to like CS101. So changing that to CS101, obviously you wouldn't want to do that. You want courses to have different names. Otherwise, our course that is actually Math 101 is now also computer science because we've hard-coded the name. So we should change that now. So yeah, this basically just creates a course class or a course object, sets the name, and just make sure that the name of the course is what we set it to be. For making sure that the list is initialized correctly as an empty list, we want to check that a newly initialized course has a size of 0. So, as we went over, size is just the length. If you have an empty course and you've only called the init, you would have an empty list which has a size of 0, or a length of 0, which is then returned by the size function, which then lets this test pass because you're checking that 0 is equal to the size of an empty list. Cool. So, making sure that an empty course has no students in it. By checking that your newly initialized function has an empty list, you are kind of checking that an empty course doesn't have a student in it. But when you add students, you want to be able to check, or when you have an empty course, you want to check that no students exist. So you're creating a course, then you're creating a student, and you're checking if the student is in the course. If the student is in the course, if the student isn't in the course, we get this -1 sentinel value or not found value that we specified in the constructor. Obviously, if we used add to add this student to the course, this test would fail. So this is just designed to check if an empty course actually has nobody in it. So obviously you also can't remove from something that doesn't have anything in it. So all that method does is basically makes a course, makes a student, and asks the course to remove a student that it doesn't have in it. It's going to throw an error and tell you, well, the student doesn't exist, so we can't remove it. So assert raises is an assert test that basically just checks if the error that's raised is a value error. So if we go back to remove, we're raising a value error, which is why that pops up again here. So knowing the different types of errors not only can help you debug, but can also help you write unit tests for your code, which is kind of neat. For testing that an empty course returns an empty string, obviously if a course doesn't have anybody in it, and we have the course defined as it is, or have the repr defined as it is in the notes, where it starts with an empty string, all that you're going to want this check, or the unit test to return is just an empty string. If there's no students, there's nothing to string build, there's nothing to add to the string, so just return an empty string and double check that it's returning that. And now there's just a couple of other tests that you're basically checking that once you add a student to the course, is it actually returning the correct size? You want the size to update correctly. So the singleton returns 1, you're adding Bob to CS101, and then you're just checking that the size is equal to 1. Same thing with returns -1, you're adding the student, and you are adding a student that isn't Bob, and you want to check that the student that isn't Bob isn't in the course, even if there are other students that exist in the course. A lot of students in courses. Yeah, a lot of these basically just go over kind of edge cases. If you would, I mean, unit tests are good. You obviously would expect your code to be working the first time. I'm sure by now you guys realize that's mostly never how it works. Even me doing print statements don't work sometimes. So, yeah, basically just the unit tests are good because they help you double check that it's working exactly the way you expect it to. You can test it yourself, but you can run into issues where your functions have side effects, maybe like you're updating something that you shouldn't be, and that might have a kind of domino effect and a compounding impact further down the line when you're trying to use the function again in other methods, I guess, or in other methods. But, yeah. yeah, so yeah, obviously, I'm sure you guys saw, obviously, yeah, like at the bottom here, you just have the student and the course unit test. If you guys want to have a look at them, feel free. But I guess now that that's done, you can go over to searching, I believe. Yeah. Cool. So, yeah, I'm sure you guys will cover this more. There's only a couple classes left, so hopefully you get through it. But this is kind of the start of where you guys are moving away from just programming to like actually doing computer sciencey things. Like it's all well and good knowing how to code, but knowing how to search for things properly, knowing the complexity of certain search functions and algorithms is like very important when it comes to, especially to industry. You don't want your Word to load in 10 minutes. You don't want your computer to take 8 minutes to boot. You want your stuff to load fast and you want it to load efficiently. And that's kind of where searching and complexity comes in. So, yeah, I guess kind of a little recap. Yeah, hopefully you guys have used Colab and know how it works. Be a bit worrisome, I guess, at this point in the semester if you didn't, but it's fine. Yeah, you know how to print, you know how to make types, you know how to assign values to variables, you've worked with lists, you know how to use conditional statements, you know how to do linear searches, you can do loops, you can read and write data to from files, so doing file input and output, also pretty important. And yeah, you can kind of look at code that might not be your own or was yours from a while ago, and you can roughly understand what it's doing. And yeah, you can go from there. And you can also test your own code, which is important. And that needs to be fixed. So yeah, basically, like at this point, you guys know a lot of stuff about programming, more specifically tailored to Python. But programming in general, a lot of the concepts extend to like using Java next semester, or if you wanted to use C++, you can. But the same ideas will apply, and searching and complexity also like spreads very far into computer science. If any of you guys are taking CS, your first course in second year, 255, is going to start looking into actually how do you calculate the complexity of algorithms and functions by hand, which if that sounds fun to you, I don't really know what to tell you. It isn't not fun, but there's definitely more fun things you can do. But I mean, hey, if that's your thing, that's your thing. But yeah, we're basically going to start looking more into algorithms and how we can actually solve problems with the tools that you guys are now mostly equipped with. So yeah, super simple algorithm, linear search. The complexity of an algorithm can be roughly interpreted by the number of loops. This is a very general statement. James will probably go over it again and be a little bit less hand-wavy. But basically the number of nested loops you have will have a huge impact on the complexity of your algorithm. If you have 10 things in a list and you're looping over everything once, your complexity is just one loop through that list. If you have nested lists and you need to access every individual thing, so think of like a matrix that you guys would have had in lab when you had to loop through everything once. That probably didn't seem like it took very long because you only had 9 or 12 or 9 or 16 or 25 things in it. If you have like a matrix of size like 1,000,000 by 1,000,000, all of a sudden you've got like a quadrillion elements in that matrix, and that can take forever to get through with like not very efficient algorithms. But depending on what you need, if you need a linear search, unfortunately you just have to check everything. So, well, unless you know where it is, but the point of using a linear search is you don't know where it is, you're trying to find it. That's the whole searching part of it. So, well, I guess I just kind of did half of this for you, but yeah, I guess like if you're looking for a haystack and a needle, or a needle and a haystack, you're just trying to see if it returns true or false. So does the needle exist in the haystack? If it does, obviously return true. If it doesn't, then you want to return false. It wasn't found. But how much space do you guys think would, like, a linear search would take up? Like, it doesn't, not in like bytes or anything, but like if the time complexity for a linear search is, if I give you a list of n things and you assume it takes 1 second per thing in the list to check it, like how much time, like it takes n seconds to get through that list if you're doing a linear search. You're only looping over the list once, which is why, so for every element in the haystack, you can assume that everything in this list, or in this loop, takes 1 second to execute. It obviously takes a lot less time, but for now we'll just assume it takes 1 second. For every element in the, for every element in the haystack, if the element is the needle, return true. If we have 10 things in the haystack, you have to loop through everything once. You also have to store this haystack somewhere. So obviously it gets stored on your computer, but it has to take up a certain amount of space. But if you're looping through everything once and it takes 1 times n seconds, so n being the number of things in the haystack, like, I guess you guys can talk to each other as well if you want, but like how much space do you think that haystack itself actually takes up? So if we have a list that has that many things in it, and we're trying to find if we just want to check if one exists in it. Obviously, you guys know how linear searches work. You've probably beaten them to death at this point, but basically, this algorithm, for every element, it needs to store the element somewhere. It has to check, okay, we're going through the list. This 0 has to be, it can't just be, when we're looping over the list, the elements that you're looping over aren't just referenced by, that you're not referencing them directly from the list. You're actually creating a new variable with element, and you're assigning whatever is in the list to that new variable. So that's taking up more space outside of just where this list exists. So for a list of 10 things or n things, you need the time. Yeah.
So is element like a copy of that thing? Like it's not, you said it's not referencing directly from the haystack. Does it make a copy of that value to play with?
Yeah, it would take the thing in the haystack and it would say, okay, cool. The value in this case, so the first one would be 0, and it would create a new variable and assign that same value. So like, yeah, it would kind of make a copy. Yeah. At least I'm pretty sure that's how it works. But if I'm wrong, I'm sure James will correct me. Yeah. Well, here actually, let me have a look. Alright, well, I don't know. It looks like maybe I lied to you. I think it is actually, it does make a reference and not a copy. So, but even though it's referencing, it still has to store that reference somewhere. So I guess regardless of how it's referencing or copying or whatever it's doing, it's still taking up space somewhere on your computer. So for a list of n things, it takes n amount of time to get through everything, to get through the entire list once. It also takes n space to loop through that list once, because you need to have enough space for every n thing in the list to exist once. Does any of that not make sense? Cool. So, yeah, we want to make sure we have a good algorithm. So what would, I guess knowing a little bit about like space and time complexity, what would be ideal for an algorithm? Like if you guys wanted to do something given some input, you would want it to probably run pretty fast and not take up a lot of memory, right? Yeah. So a lot of CS research, and more kind of on the theory side, but also in the practical application, but a lot of efforts being put into generating efficient algorithms for solving problems. So you have what do you have? Maybe this is a bit too much for 161, I guess, but we can talk about P and NP. So P versus NP is basically a really big deal in computer science. It's one of the questions posed by a math institute, basically. And what it's asking and what it's saying is there are problems that exist that have solutions, and we can check solutions in polynomial time. That's P. NP doesn't stand for not polynomial. It's non-deterministic polynomial time, but you guys don't have to worry about that. Basically, the gist of it is people have been trying to prove for years that problems in P are the same or different one way or another than problems in NP. So NP problems take an arbitrarily long amount of time to find a solution, but you can check the solution in polynomial time. So polynomial time just means like you can check it in linear. So n, you can check it in quadratic, like n squared. You can check it in cubic time, n cubed. As long as the size of the input as like a complexity is not an exponent, that's polynomial time. So if it took like 2 to the power of n like actions to check a solution, that's not polynomial time at all. Hi. So yeah, basically a lot of efforts being poured into trying to prove one way or another that these very difficult to solve problems can be solved and checked in polynomial time. So something like the traveling salesman problem, where you have a bunch of cities and you want to find the best route through all the cities while only going through every city once and ending up at the same city you started at, is an NP problem, because if you have like 50 cities, you have 50 factorial different ways of going through all of those cities, which if any of you guys were in lab a couple of weeks ago, you would know that that's more possibilities of, or more permutations of cities than there exists a number of atoms in the universe. So it's a lot, but anyways, yeah, we're out of time, so thanks.